When you type a prompt and an image appears, it's tempting to imagine the AI painting it stroke by stroke, or quietly copying something from a giant library of pictures. Neither is true. It starts from pure random static, the kind of fuss you'd see on an old television, and gradually removes the noise, guided by your words, until a picture emerges. It doesn't draw, it denoises. Let's see exactly how. Watch the field on the left. It begins as pure noise, and step by step, we subtract that noise until an image sharpens into view. That single move, sculpting a picture out of static, is the whole idea behind diffusion. Over the next few minutes, we'll trace it end to end. How the noise gets added, how a network learns to take it away, how your text steers the result, and the clever trick that makes it fast. It doesn't draw, it denoises. Let's clear away the two wrong pictures first. The model is not an artist laying down brushstrokes on a blank canvas, and it is not a search engine pulling a matching photo from a database. There's no canvas, and there's no folder of images. What actually happens is stranger and far more elegant. So let's build it up properly. Here's the core reframe. Start with a square of pure random noise and ask a simple question. What would this look like with a little less noise? Remove that slice and ask again. Watch the step counter climb and the noise bar drop on the left, frame by frame. Nothing is being invented from a reference. The shapes you see were hiding inside the randomness all along, waiting to be revealed. The image you end up with was never stored anywhere. It was carved out of static, one small subtraction at a time. The forward process, making noise. To learn the reverse, we first study the forward direction, and the forward direction is easy. Take a real photograph and add a sprinkle of Gaussian noise, small random values, drawn from the familiar bell curve. Add a little more. Keep going for many steps, and the picture dissolves into pure static, exactly like the field on the left is doing now. At each of those steps, we now have a pair, a noisier image, and the noise we just added. That corruption, run on millions of images, is how the training data is made. Look at the three frames: a clean image, a half-noised image, and pure static. Each step just nudges every pixel a touch toward random, a tiny, gentle amount. Anyone can corrupt a picture this way. It takes no intelligence at all. The real magic, the thing we have to train, is learning how to walk that process backwards. The reverse process, a denoiser. Now the heart of it. We train one network whose only job is to look at a noisy image and predict the noise that was added. Because we build the training data by adding that noise ourselves, we know the exact answer, so we can score every guess and nudge the network until it gets good. Once it's trained, we run it many times. Predict the noise, subtract it, and repeat from fresh static, and a clean image emerges on the left. The same network handles every step, from heavy static down to the final polish. Follow the loop. A noisy image goes in. The network, usually a UNet, a U-shaped network, and increasingly a transformer, predicts the noise it sees. We subtract that prediction, and out comes a slightly cleaner image. Feed it back in and do it again. The model never predicts the picture directly. It only ever predicts the noise to remove. That's the whole trick. Text guidance, steering it. So far the image could be anything. To get what you asked for, we steer the denoiser with your words. It's the same loop you've been watching. But now every single step is gently pulled toward the prompt at the top. Type a cat in a hat, and the static doesn't resolve into just any picture. It resolves into that. The prompt is the hand on the wheel. How do words reach a network that only understands numbers? First, a text encoder. Typically CLIP, a model trained to line up images with their captions, turns your prompt into an embedding, a vector that captures its meaning. That vector is then injected into the denoiser through a mechanism called cross-attention, which lets each patch of the image look back at the words and ask which of them it should pay attention to. This happens at every layer and every step. So the noise the model predicts is always conditioned on what you wrote. There's a dial for how strongly it listens, called the guidance scale. Under the hood, classifier-free guidance runs the prediction twice. Once with your prompt, once without, and then exaggerates the difference between them. Turn the dial up, and the image clings tightly to your words. Turn it too high, and it grows oversaturated and harsh. It's a balance between obedience and naturalness. Latent diffusion. Why it's fast. One problem. Denoising every pixel of a big image, dozens of times over, is painfully slow. The fix is the idea behind Stable Diffusion. Instead of working on the full picture, we run the entire noise and denoise process on a small, compressed grid, a latent, like the chunkier field on the left. Same loop, a tiny fraction of the numbers, so it runs fast enough for everyday use. Here's the trade. A full image might be 512 by 512, over 250,000 pixels. A VAA, a variational autoencoder, squeezes that down to a 64 by 64 latent, a compact sketch that keeps the gist and throws away the redundant detail. That's dozens of times fewer numbers to push through the network at every step. We diffuse entirely in that small space. Then a matching decoder expands the finished latent back into a full, crisp image. The denoising got cheap. The quality stayed. The knobs, steps, and guidance. When you actually generate, you control two main dials. The first is the number of sampling steps. How many times we predict and subtract on the way from noise to image. Here we've set it to 20. Fewer steps finish faster, but leave the image rougher. More steps polish it, at the cost of time. The second dial you already met, the guidance scale. Think of each step as removing one thin slice of noise. With too few steps, the image stays muddy and unfinished. Add more, and it sharpens. But past a point, extra steps cost you time for almost no visible gain. In practice, most images land somewhere between 20 and 50 steps. Speed, quality, and prompt adherence. You're always trading among the three. Pushing the dials, and where it breaks. Let's get hands-on with that guidance knob. Watch the needle on the left climb. Down low, around 2 or 3, the model barely listens. The image drifts loose and ignores half of what you asked for. As we turn it up into the green band, roughly 7 to 12, it locks onto your prompt while still looking natural. That's the sweet spot most tools sit in, but keep cranking, past 15, and the gain overcorrects. The colors blow out, skin goes plastic, edges turn brittle and harsh. Higher is not better. The whole skill is finding that band where the picture obeys your words without tearing itself apart. The second dial is the number of denoising steps, and it trades quality against time. On the left, 4 steps, fast. But you can still see grain the model never finished clearing. On the right, 50 steps, clean and smooth. And yet it cost more than 10 times the compute for that last bit of polish. For years, you simply paid that price. The newer trick is distillation, where a fast student model is trained to copy a slow one, reaching a near-clean image in just 2 or 4 steps. That is exactly what powers those live previews that update almost as fast as you type. And here's the failure everyone has seen. The hand with too many fingers. Why does such a smart system trip over counting? Remember what the denoiser actually does. It nudges each little patch until that patch looks locally believable. A finger next to a finger is perfectly plausible, so it happily adds one more and one more. Nothing in the loop ever steps back to count the whole hand. Each region looks right on its own. Only together do they go wrong. That is why fingers, teeth, and repeated patterns are the classic giveaways, and why newer models work hard to teach that missing global sense. Noise to image. Traced. So let's trace the whole thing in one breath, with the prompt steering it on the left. Start from pure random noise. At each step, a unit predicts the noise, and we subtract it, repeating around 30 times. Every step is steered by your prompt, turned into a vector by a text encoder, and fed in through cross-attention, with the guidance scale setting how strongly it pulls. And the entire dance happens inside a small compressed latent space, then gets decoded back to full pixels at the very end. No painting, no database, just noise, patiently removed. So the next time a prompt turns into a picture, you'll know what really happened. The model didn't draw it, and it didn't fetch it. It started from static and denoised its way to your words. That's diffusion. Strange, simple, and a little beautiful once you see it. Subscribe for more such intuitive videos